This is the Hubble Deep Field. This is a picture taken by the Hubble Space Telescope, and they went close up on this area, you see. And see every little dot that you see in this picture?
Who's filming? No one? Oh.
Every little dot you see in this picture is a galaxy. Except for that one. That's a star that's in front, that's in between where the picture's being taken. This is called the Hubble Deep Field. No, I'm sorry, this is not the Hubble Deep Field. This is the Coma Cluster. It's a cluster of galaxies. A bunch of galaxies all together. Isn't that amazing? Every little dot is a galaxy. Could be as big as the Milky Way. And look at all of them. Edwin Hubble, he did a lot of research on galaxies, and they named the Hubble Space Telescope after him. And he came up with 4 main different types of galaxies. The first type is like ours. It's called spiral. Here it shows 3 different types of spiral galaxies. And he called them SA, SB, and SC. SA are spiral galaxies with real tight arms. The arms are tightly wound around the center. So the arm curves tightly in. It's like the arms are held tightly in. SB, the arms are held less tightly. And SC, the arms are held only loosely. So there's a lot of space between the center and the arm. It's not curved in as much. So S means spiral, and A, B, and C mean how tightly the spiral is held. That's the first type of galaxy. Spirals. Put them up here so you can see.
A is the tightest.
Yes. SA, SB, and SC. A is tightly, arms held tightly. C is arms held loosely. Again, a galaxy might be 100 billion stars or more. Our galaxy has about 400 billion stars. Oh, there's SA. That's another SA. That's called the Sombrero Galaxy.
Sombrero.
Yeah, it's the Sombrero Galaxy. There's an SB. I guess I don't have the SC in place. So those are spiral galaxies. Now there's another type called a barred spiral. And barred spirals look like this. They look like the TIE fighters from Star Wars, sort of. They have their center bulge, and then they have these bars coming out of the center bulge. And then the spirals come off of the bars.
So what are each of the classifications?
So SB means sparred viral.
You said sparred viral.
Barred spiral. Barred spiral. Sorry, it's hard to talk. So barred spiral is the next type, SB. And again, you have SBA, SBB, and SBC. I guess it's capital B. Those are barred spirals.
You can get an apartment.
The barred spirals have this bar. You see the bar that kind of goes through the middle there? And the arms come off of the bar. Doesn't it look like there's a bulge and a bar going through there? Here you can kind of see there's a bar running through the middle.
So what do I write down for each of
Well, this is just another classification Hubble had for his galaxies. Some of the galaxies he saw are called spirals.
So how do you tell the difference between the classifications of the barred one?
Well, it's the same way. A has tighter arms, C has looser arms, and B is in between.
Wait, but it looks like the opposite.
See how this arm right here is held tightly in?
Oh, yeah, I guess it's
And
true.
these arms right here kind of go out. They're not curving in. Does that make sense?
Yeah.
We actually believe the Milky Way is a barred spiral. That's something you didn't know. We think the Milky Way is an SB, not an S. And throughout your entire life, if you were ever heard anything about it, you probably heard the Milky Way is a spiral galaxy. We think it's a barred spiral.
Like A or B or C? Put it on there.
That's a good question. I think it says in here.
Do you believe that? Do you believe that?
No.
Stupid for doubting that you didn't get it. I know you're not gonna get it. I can trade.
Suggests that the Milky Way may be a barred spiral of type SBB or SBC. However, the full extent of the bar remains uncertain. But they don't know for sure. It's hard to tell what we are because we're in it. You can see, it's so big you can't. It's hard to make sense of it. It's easy to tell by looking at these because they're far away and you can see the whole thing. It's kind of like if you never had a mirror or a reflection, you wouldn't really be sure what you looked like. Although it's easy to tell what other people look like. Then there's ellipticals. Again, I don't have time for all those notes. An elliptical galaxy is the third type.
Underneath the picture. Is it ET?
That's a SB, SB.
Elliptical galaxies are called E. And they go from E0 to E7. I'm sorry. From E0 to E7. E0 all the way to E7. So there's E1, E0, E1, E2, E3, E4, E5, E6, E7. E0 is the most circular of elliptical galaxies. And E7 are the most elliptical. Do you know what an ellipse is? We've talked about that shape before.
Wait, you said E0 are the most what?
E0 are the most circular. And E7 are the most elliptical. How would you explain the shape ellipse to somebody you didn't know anything?
Oval.
Yeah, flattened circle.
What causes the difference?
Well, what causes these shapes is not fully understood. But we don't really worry about that. We're just classifying the shapes. The ellipticals have a huge range of sizes. They can be small to incredibly large. There are elliptical galaxies that are 10 times as big as the Milky Way, with trillions of stars. Even more than that. The biggest galaxies we see are ellipticals. There's an E2. Look at that. E3. E5. You see how it's a lot more flattened? That's billions of galaxies. Billions of stars, I'm sorry. looks like a cloud out there. Hold on. Let me come back to these. The next type is irregulars. Irregular galaxies don't fit into any of these three categories. And they have basically two subdivisions. There's irregular 1 and irregular 2. IRR is used for irregular. And then Roman numeral. So irregular 1 and irregular Roman numeral 2. Irregular 1 look like misshapen spiral galaxies. Irregular 2 have other peculiarities and problems. So if it looks like a spiral galaxy that's been weirdly shaped, we say it's irregular 1. If it looks just strange, no relation to a spiral galaxy, we call it irregular 2. A lot of astronomers call irregular 2 galaxies train wrecks. They say it looks like a train wreck. You know what? You ever heard that term before? Train wreck is, I mean, if a train wrecks, you got cars everywhere, pieces flying everywhere. It's just a jumble, a mass jumble that's just random. So irregular 2s look like train wrecks.
So we will become that one day, maybe?
If we're lucky.
Well, that's the next thing is how do these galaxies get the shape they are? And we think it's because of collisions between galaxies. See, galaxies can collide with one another. Galaxies move through space, and they can hit one another and change their shape. And galaxies move way too slow for us to see a collision occur and see what results. Most of the way they've figured this out is through computer simulation. They can simulate now with supercomputers millions of stars in the shape of a galaxy, and take another galaxy simulated on the computer with millions of stars, and have them move and run into each other and see what comes up. They think that the irregulars come about because of collisions. There's an irregular galaxy. That's the Large Magellanic Cloud. That's an irregular galaxy that orbits around the Milky Way. And it can be seen with the naked eye from the southern hemisphere. It's the only galaxy that can be seen with the naked eye. This one and the Small Magellanic Cloud. Other galaxies can't really be seen with the naked eye. You need binoculars or telescopes. Here's a couple others that are irregular. That thing there is a different shape than we normally see. Here are the two Magellanic Clouds. That's the Small Magellanic Cloud, that's the Large Magellanic Cloud, and that's what they look like in space. They kind of sit near one another in the sky. I thought I might have a picture of them from the ground. Yeah. This is a picture just taken with a nice camera that they left the, they took a long exposure, but you can see there's a tree, and there's the Small Magellanic Cloud, and there's the Large Magellanic Cloud. So that picture's a lot brighter because they left the shutter open for a long time to get more light in. So you can see all these background stars show up. There's really not that many stars visible in the sky. But you can see those two with the naked eye. Oops. and here's where they sit. This is the plane of our galaxy. That's the Milky Way. And this isn't a picture, this is a computer simulation. It's showing how the Milky Way would be sitting. And here's the small and large Magellanic Clouds. They kind of sit down below the plane of the Milky Way. And they're best seen from the southern hemisphere because the Earth lies kind of diagonally orbiting our sun with, it's kind of actually diagonally this way. But the southern hemisphere faces down, and the northern hemisphere faces up. Oh, there's two more I need to tell you about before we get into the Hubble sequence. I skipped over them. There's two more I'm going to put on the side over here. They're called S0 and SB0. What does S mean? Spiral. But 0 means, it's not SA, it's not SB, it's not SC, it's S0. 0 means it doesn't have spiral arms. It's like a spiral galaxy without the spiral arms. It kind of looks like a flying saucer. So if I was going to draw a spiral galaxy looking from the side, I kind of draw it like this, right? But if you take off those spiral arms, then it kind of looks like this. That's an S0. An S0 is a cross between spirals and ellipticals. It's almost an elliptical, except it's got this dip in it. Whereas an elliptical would be more circular. It wouldn't have these dips. S0 is a spiral without any arms. And you also see barred spirals without any arms. SB0. That's just take the arms off of a barred spiral, take the arms off a spiral, and you end up with S0 and SB0. There's an S0 right there, and there's an SB0 right there. To me, that just looks like an elliptical.
So the SB zeros is just like a circle, kind of looks like Saturn.
It does. It's got the bar, but it doesn't have any spiral arms. It's like they had a barred spiral and they just took the spiral arms off. So Edwin Hubble took all this information and he made a nice little diagram called the tuning fork diagram. This is called the Hubble sequence. And this is a good way to memorize all the galaxy shapes. So, y'all know what a tuning fork is? You know, you hold a tuning fork and you hit it and it goes doo. It's real annoying. Doo. Isn't that annoying?
Yeah.
So this is like shaped like a tuning fork. It's called the Hubble sequence. E0 is at the end, all the way up to E7. Those are the more ellipticals. These are the more round. And then S0, that's this one. That's the spiral without the arms. He put that there. And then the SA, SB, and SC with the tighter arms to the looser arms. And the SBA, SBB, and SBC with the tighter arms to the looser arms. And then the irregulars he put in between because he didn't know where those fit. He was thinking in his head that maybe the ellipticals change into spirals somehow. And so he saw this kind of progression. We find out that galaxies can change and become spiral through our computer simulations. Let me see what this is. I don't know what this is. showing is looking at galaxies at different stages in time. It's very interesting the way the speed of light works. Y'all know light moves at a certain rate, right? So if you take a telescope and you look at something really, really far away, you're looking back in time. Because it might have if it took the light 10 billion years to reach your telescope, you're looking at it as it was 10 billion years ago. So when we take our big telescopes and look at something real far away, we're seeing back in time. And you can literally look at galaxies. The universe is how old? Do anyone remember how old the universe is?
13 billion.
About 13.7 billion years old. And we have telescopes that can see almost that far back.
How can a telescope see back into time?
Because light takes a long time to travel, you see.
This is not. I can't do it.
So if I look at something real far away, it happened, I'm seeing it as it was a long time ago. Did you know you're not seeing me as I am now? You're seeing me as I am 10 nanoseconds ago?
I'm not good at this. I can't comprehend.
You're not good with that?
No.
Hey, I was cool 10 nanoseconds ago. I'm pretty lame now.
I just can't comprehend this at all. Like, it just not.
Well, you're going to have to, because it's going to be on the next test. So, here's what galaxies looked like a billion years after the universe formed. And if you go forward in time, what do you notice about these galaxies?
They get bigger.
They're getting bigger. Very good. That's what Hubble noticed.
I'm sorry.
So how could galaxies get bigger over time?
They grow
How could they grow?
by
We
exploding.
collect matter.
By collecting more matter and by galaxies merging with one another. There used to be a lot more tiny galaxies, and now there's a lot fewer bigger galaxies. The galaxies come together to form larger galaxies, you see. Gravity pulls them together. And so that's exactly what we see as we move through time, viewing through time. Small galaxies become larger over time. Is that interesting? Galaxies merge. And this is what our local group looks like. We are in a local group of galaxies. And here we are, there's the Milky Way. And every little dot you see here is galaxies that are near the Milky Way. And let's blow that picture up and look up here. This is similar to that star chart we were working on that you're going to finish in lab the next time we do lab. Here's the Milky Way in the middle, and we're a pretty big spiral galaxy. Yay, us. And there's Sagittarius Dwarf is the nearest galaxy to us. It's hard to see because it lies right on the same plane of the Milky Way. Ursa Minor Dwarf, Draco Dwarf, Sculptor Dwarf. There's the small and large Magellanic Clouds that I discussed. They're going around the Milky Way too. Sextans Dwarf, Carina Dwarf, Fornax Dwarf. These are all little galaxies. The reason why they're called dwarf is because they're dwarf galaxies. They're small galaxies that might only contain a few million stars. Only a few million stars. That's a lot. And so we got all these little galaxies orbiting our galaxy. And then if we look across over here, there's another group kind of like ours with the Andromeda Galaxy. As a major galaxy, the Andromeda Galaxy is about the size of the Milky Way. And it's got a bunch of little galaxies here going around it. M32, M33, and 3, I don't know what that means. Andromeda 3, I guess. And anyway, this group of galaxies and this group of and our group of galaxies are both kind of going around one another, you see. Their gravity pulls on one another, and they're kind of in this cosmic dance. This occurs over hundreds of millions and billions of years. And scientists have calculated that our galaxy is going to hit the Andromeda Galaxy. they're going to run into one another and probably merge together. And all these little galaxies will probably merge too with the bigger ones. And it'll all be one big galaxy after a while. They calculate that this is going to happen in about 6 billion years. You won't be around. And by that time, our sun will have already expanded and engulfed our planet. And then cast off its outsides and become a white dwarf. So our solar system will be very different by the time these galaxies merge, but it's going to happen eventually.
So most stars at night, like all the see, are the stars like in those galaxies?
No, the stars that you see at night in the sky are all in the Milky Way.
Oh, okay.
These galaxies can't be seen with the naked eye. You have to have a telescope.
Can you see the stars inside them or just the galaxy?
With your telescope, if you have a big enough telescope, you can see some of the stars inside of them. But most of these galaxies are so far away that even the Hubble telescope just sees it as a dot.
Can you see any like planets or anything inside?
We can't in other galaxies.
And
But we suppose that there are. Let me go back and show you this picture that the Hubble took.
can we see anything else out of the Milky Way? This aside from those galaxies.
We can see stars in the Magellanic Clouds. Again, this is a picture taken by the Hubble. And this is, every little dot you see there is a galaxy made up of billions of stars. So we can't see any individual stars inside that galaxy. We can barely see the galaxy. But it is made of stars. Because there are galaxies that are closer, like the Magellanic Cloud, and we see that you can see the individual stars in that galaxy. What were you trying to ask? I didn't quite get it.
We could see anything without telescopes outside of the Milky Way?
The Magellanic Cloud, with the naked eye,
Or do they-
the Magellanic Clouds are the only thing.
That's the only thing?
You can't even see the Sagittarius thing though, so close.
There are some, no, because it's on the same plane of our
Never
Milky
mind.
Way, and you can't see through all the junk to see it. There are some people that brag that they can see the Andromeda Galaxy with the naked eye. They claim to have very good eyesight. So there's the small and large Magellanic Clouds are big enough where from the southern hemisphere you can see them with the naked eye. But none of these others are big enough where you can see them with the naked eye. Some people say they can see Andromeda with the naked eye. On the darkest night in the darkest corner of the earth, if you're looking towards Andromeda, some people say they can see a smudge of light. A little smudge on the sky, and that's Andromeda.
Liar.
I don't know if it's true. I think they might just be making it up. How do you know if they're lying or not?
Take out the
So, there's what Andromeda looks like. If you could see it up close with a telescope, that's what it looks like. And that's a galaxy that's going around Andromeda. So is that one.
I need to finish it. Did you finish it?
Let's see what else I need to show you. Oh, let's go forward. Okay, so this is a map that scientists have made of space, and the Milky Way would be right there. The Milky Way is a dot right in the middle of the middle box. And near us is a huge cluster of galaxies called the Virgo cluster. And the Centaurus cluster is over here. And the Hydra cluster is over here. We're not really in a cluster. We're kind of sitting, our galaxy kind of sits somewhat alone in space. Every dot you see here on this page represents a galaxy. And one box is 10 megaparsecs in size. That's 10 million parsecs. which is 33 million light years. So from here to here is 33 million light years.
Is this box as far as they can see in terms of galaxies?
No. This is just a small portion of what they can see in terms of galaxies.
So why is there a big empty space on the top right, left, and bottom?
Oh, here?
Yeah.
Yeah, they can't see them as good. They don't have as much data from here. And they haven't pointed their telescopes in all areas either. So this is just mapping some of them, some of the areas. And some of these famous scientists, there's Hubble, if you're wondering what the Hubble Space Telescope's named after. It's named after this guy. He noticed that when you're looking at these galaxies, galaxies that are far away tend to be moving away from us. It is true all over the sky. And the further away the galaxy is, the faster it's moving away from us. He knows this by the Doppler redshift. Every galaxy is redshifted in its light. That means it's moving away from us. Remember the Doppler effect? We already studied it. I'm not going to re-explain it. Oh my gosh, he freaked out and said. What does that mean? It's one of the biggest discoveries in the history of thought. It has huge implications. If every galaxy is moving away from us, what does that mean? They're scared of us?
The universe
They're running away because they're scared of the Milky Way? Probably not. What it means is that the universe is expanding. Did you just say that?
Yes, I
I'm
did.
sorry. I didn't hear. The universe is expanding. And space is stretching. It's kind of like if you took a balloon, I wish I had a balloon here, and you blew it up. The balloon gets bigger. And if I had drawn a bunch of dots on the balloon, the dots would spread out from one another, wouldn't they? Every dot is spreading out from every other dot because the universe is expanding. Hubble discovered this. Ooh, we don't really know. Nobody knows. It just is. But when Hubble discovered the universe was expanding, quickly some big thinkers of the time, Hubble too, said, wait a second, if the universe is expanding this way, what if we rewound and went backwards in time? What was the universe like? At one point it must have been very small. That's the Big Bang Theory. The Big Bang, not the TV show, it's a good show. The Big Bang Theory means that the universe is expanded from a very small universe, an infinitely small universe, if you can believe that, smaller than the smallest atom. The universe has steadily got larger and larger until it is the size now. You know how long it's taken for the universe to stretch out till it is the size now? 13.7 billion years. They can rewind it and get that number. It's math. They find out how fast these things are spreading apart. They must have all been together 13.7 billion years ago. That's how old the universe is. What a huge discovery. Suddenly, before Hubble, you go from thinking that the universe is infinite and has probably been around for who knows how long, to knowing exactly how long the universe has been around. That's the Big Bang Theory. It's not a bang like you throw a firecracker and it blows up and moves stuff everywhere. It's an expansion, is all it is. That's what the universe has done. For some reason, scientists don't know why, the universe has expanded from a point.
If it was that small and there was enough space for it to expand, could there be another universe?
There might be. There might be other universes outside of our universe. We have no way of knowing, really, right now, whether that's the case. Are we the only universe? Or is it like a room full of balloons, all which are expanding? Maybe some are contracting. Who knows? Maybe our universe will expand and then it will contract. We don't know. Chapter 17 talks more about that. That's cosmology, and it's kind of like, whoa, way out there. You shouldn't do heavy drugs before you come to those classes. It might totally freak you out. What were you going to say? 13.7 billion years old. So we call that Hubble's law. Hubble figured out how fast the universe is expanding. This is Hubble's concept. 70 kilometers per second per megaparsec.
Will you please leave it on the slide? This is like so much fun.
70 kilometers per second per megaparsec. What does that mean? That means in 1 megaparsec of space, which is 3.3 million light years of space, two objects will be moving apart from one another. If they're separated by that much space, they'll be moving apart from one another at 70 kilometers per second. 70 kilometers per second, the speed of a bullet is like 1 kilometer per second. It's less than that. The speed of a bullet is much less than that. A tenth of a kilometer per second. So we're talking a spreading of space a lot faster than bullets go. 100 times faster than bullets go. It's fast expansion. And so if you're 2 megaparsecs away from someone, how fast will you be moving apart? If you're 1 megaparsec away from someone, you'll be moving apart at 70 kilometers per second. If you're 2 megaparsecs away from someone, how fast will you be moving apart from them? 2 times 70. 140 kilometers per second.
Why is it double?
They're both moving.
Because for 1 megaparsec, this unit is per megaparsec. So for 1 megaparsec, you're moving apart at 70. If you're 2 megaparsecs apart, you're moving apart at 140. You double the distance, you double the rate at which you move apart.
Does that
Does that make
kilometers per
sense?
second per what?
You're 10 megaparsecs apart.
Megaparsec?
10 megaparsecs apart, how far are you spreading apart? 700 kilometers per second. So, you can imagine if you get enough megaparsecs apart, you'll be spreading apart from one another at faster than the speed of light.
Will you explain what redshift is?
And that means you can't see the object that's that far away. Because its light will never reach you.
Redshifted spectra? What does that mean?
No, the expansion of the universe can actually happen at faster than the speed of light.
Wait, won't it still reach you?
It will not. Because if you are moving this way, way over here, and you are moving this way, way over here, and this thing releases light, that light will never get to you because you're moving that way faster than the light is moving. The space expands faster than the light can travel. So that means there's an area of space that's going to always be dark, where we'll never be able to see that far away. And that can be found out mathematically by using Hubble's constant. Yes?
So redshift, I know that it's like the Doppler effect or whatever, but like I don't understand why. How is that? Like why? Or you just say that the Doppler effect. Why is it called redshift? Like why is it something different? Why?
Because if something's moving away from you and you bounce something off of it, it comes back slower. And so we say that the spectra is shifted to the red part of the spectrum. The little lines. We studied redshift a long time ago. Remember the lines of the spectrum? Those are shifted one way if something's moving away from you. Because the light will come back at different wavelengths.
How much is 1 megaparsec?
I'm not comprehending this at all.
A parsec is 3.3 light years. So a mega is a million. A million parsecs. 3.3 million.
So a parsec is 3.3 light years.
A parsec is 3.3 light years. A megaparsec is 3.3 million light years.
Megaparsec, which is a million parsecs.
Yeah, mega means million.
Million parsecs.
Look at Hubble. You always see him smoking his pipe.
Wait.
He loved his pipe. I can't. I have to go on. Here's his telescope.
And his pipe.
See, he's got his pipe. I told you, I'm not making this up. I've never seen a picture of him without a pipe.
Trademark.
And here it shows Ellie the redshift. This Virgo, these little lines, see those little lines in the white cloudy area? There's two little lines.
Yeah.
Those lines shift to the left, to the red part of the spectrum. The further away the galaxy is, those lines are further shifted. Those are hydrogen absorption lines. And that means the hydrogen gas in the Virgo cluster is moving away from us at a slow speed, but the hydrogen gas in the Hydra cluster is shifted way over this way to the red part of the spectrum. And we can tell by how far it shifts how fast it's going. 61,200 kilometers per second away from us. It's receding from us at that rate. It's a simple relationship which you can graph. The further you are away, the faster you'll be receding. Period. Scientists think that it's because space is expanding. For some reason, empty space doesn't just stay still. It expands, again, like a balloon stretching. And so as the space expands, the universe gets bigger. Why does it expand? They theorize there's an energy that they call vacuum pressure. It's also known as dark energy because they don't know what makes it. Maybe it has something to do with dark matter. Most of the energy in the universe is dark energy. And most of the matter in the universe is dark matter. And we don't know what either of them are. Whoa. Isn't that crazy? Now, back to galaxies, because we're going to talk about this cosmology stuff later. But the last thing about galaxies is some galaxies, especially ones real far away, have real active centers. We call them active galaxies. And there's a bunch of them. There's Seyfert galaxies and radio galaxies and quasars. These are all active types of galaxies. Ellie, I'm going to give you this whole thing right after the bell rings, okay? And man, these galaxies, they give off crazy energies. Some of them have these giant radio lobes. They give off a bunch of radio waves. We call them radio galaxies. And some of them they call quasars. They give off a huge amount of energy, even though it's a galaxy real far away. That's what they were talking about in the video. And I'm kind of ruining the video a little bit here for you, but that's okay. We know that the reason why galaxies are active and give off a lot of energy is because they have a giant black hole at the center. And the black hole is feeding. When galaxies are very young, there's a lot of stuff that's falling into the black hole. And if material is falling into a black hole, it's kind of like when you're going down a drain. You ever watch water go down a drain? It kind of curls around slowly, and then as it gets near the middle, it speeds up. And in young galaxies, there's a whole lot of material falling down the drain of this black hole and spiraling faster and faster and faster until it heats up real hot, and then some of the energy goes shooting off perpendicular to the plane of the rotation here. And that energy that comes shooting off, if it's facing us, if the galaxy is situated in such a way that these beams that come shooting off hit us, we see it as an active galaxy. And a lot of these real old galaxies are active because that's what a galaxy is like in its youth. The Milky Way was like this. When the Milky Way was young, the black hole at its center was feeding on this material, and this material would come into it and get eaten up. Now that 10 billion years have gone by, or 13 billion years have gone by, our galaxy we think is about 10 billion years old actually. It's not as old as the universe. Now that 10 billion years have gone by, our galaxy's not feeding much anymore. It's already eaten up all the stuff that was near the middle, and there's kind of a blank space around the black hole that's in the center. There's not as much there. So our galaxy is not an active galaxy anymore.
Wait, the universe is how many?
13.7 billion years old.
And we think that 10 million?
10 billion.
10 billion?
Our galaxy is probably 10 billion. So galaxies that are young are usually feeding and active. And galaxies that are old are not feeding. So none of the galaxies near us are active. Only ones real far away, because those are the ones that are real old. We're looking back in time. We're looking when galaxies were young, they were active. And so things like quasars that they talked about in the video, and radio galaxies, and these Seyfert galaxies you'll read about, those were all active galaxies. And our Milky Way was probably like that when it was young. It was an active galaxy with this massive, supermassive black hole at the center. Every galaxy has a supermassive black hole at its center that's billions of suns in mass. And it just took in lots of material and got big, and that's what lies at the center of every galaxy. And that explains all the active galaxies that they'll talk about in the reading. Let's see an active galaxy. Or not. Oh, there's an active galaxy. Look at it blowing all that stuff away. Here, I'll speed it up for you. Look at that. Look at that galaxy. Huh? Nah, you don't care. Read chapter 15.
It's not turned up.